Ngalakin Khadijan Nyunga Boja.
Okay, today we are going to look at lecture 7, which is the second part of the DC electrical machines. You can find corresponding lecture notes in the online lecture notes part 2, but now it's from page 15 to 24. Previously, we have spent 2 lectures introducing the fundamentals and some details of the DC machine. There are several key points. Let's briefly recapitulate it here. Firstly, we are looking at the rotor circuit, or we say the armature circuit, rotating in the stator's magnetic field. This rotor circuit, firstly, it has conductors carrying current. And because of this, we have a force developed, and that force produces the torque. So the torque, if we use torque to represent torque, is equivalent to the machine structure constant K times the flux, field flux times the armature current. So this is the torque. And when the torque is exerted on the conductors, on the rotor surface, it is going to create the movement. And with the moving conductor, and we see the moving armature circuit, what we have is a developed electromotive force. This is the electromotive force. It is a voltage, and this voltage is, again, if you derive this expression, it's going to be equivalent to the machine construction constant K times the flux times, this time is the rotational speed of the machine, no longer the current. This is the first thing that is important. Secondly, we also look at the magnetization curve. We know that the magnetization curve for DC machine can give us some information. And we have several different magnetization curves. One of them is the developed electromotive force versus the field current. So at different speed, we have different magnetization curve. So this is the curve for speed omega 0. This curve tells us that if we want a certain electromotive force developed, how much the field current we want. And we can control the field circuit to deliver the field current to produce the electromotive force. Now, if we want to figure out the electromotive force of the other speed, for example, electromotive force for speed 1, we can simply use the proportional relationship where EA0 over EA1 is equivalent to omega 0 over omega 1. Why? Because we have this equation here. It's going to be the full version of this equation is going to be K phi omega 0 times over K phi omega 1. So K phi cancels, and that's what we have, the proportional relationship between the speed and the developed electromotive force. This is the second point. And the third point is we looked at the equivalent circuit. A simple version of the equivalent circuit of the armature is something like this. Firstly, we have the external voltage source. Assume this is the external voltage supply, and this produces current that goes through the armature inductance, but usually we ignore this armature inductance because it's very small, and we have armature resistance, and then we have induced electromotive force. This is the equivalent circuit. We also introduced several important phenomena like the commutation in the DC machine and the armature reaction, and how to use compensating windings to overcome this. This is a brief summary of the key points we have learned until now. Now, let's look at what we're going to talk about today. Firstly, we'll be looking at the relationship between output power and the size of the DC machine. When you try to select a DC machine for a certain application, probably the most important things for you might be, firstly, output power, because you must be able to deliver the power to drive the load, right? So if you know the load required power, the output power, nominal output power has to be equivalent or slightly above that. Secondly, we want to know the size of the DC machine that can deliver the power. Most people prefer compact design, because if you can have a small size DC machine, you don't want a huge size DC machine doing the same job, because it's going to increase the volume and possibly increasing the weight of your system. This is undesirable. The second point we are going to cover today is the speed control of the DC machine. We want excellent speed control, especially your DC machine is used as the servo motor, where the precise speed control is required. We're going to look at how to explore the torque speed characteristic curve and do the speed control. The third point, three-dimensional demonstration of the armature reaction compensation. If you remember, previously we mentioned armature reaction, and there's one drawback of the armature reaction, as we mentioned before. It's called drawback 1. Because of the armature reaction, we have distorted magnetic field. So when your rotor rotates to this position where the two conductors are, current carrying conductors are in a vertical surface that is perpendicular to the magnetic flux, because of the presence of the armature reaction, at those 2 points, the flux density is not zero. So the induced electromotive force is not zero. And this electromotive force dropped on a very low internal resistance is going to give us a huge current. And this current generally sparks at the joints of the commutator and the brushes, shortening the lifespan of the commutator and the brushes. But this is only one drawback. Today we are going to introduce the second drawback. Drawback 2. What is it? It's called unwanted flux field weakening. Some people are also calling this flux weakening. We have to say that in AC machines, field weakening is wanted because that's how you obtain a higher speed upper limit for AC machine. But for the armature reaction-induced field weakening in the DC machine, we don't want it. Why? Because it can result in the unstable speed control. Later we're going to explain further what is the mechanism and how the compensating winding also helps with this. The final point, starting circuit and transient of DC machine. For starting circuit, most of the DC machines needs this starting circuit to limit the starting current. Otherwise, the starting current is just too high. And if you are looking at a large motor where it takes a long while for the machine to rotate to up to a high enough speed, this starting current will last long and damage the machine. As for the transient, what does it mean? When we talk about transient, basically we are talking about the rate of change of something, right? Because with the rate of change, you create the variation. It might be the rate of change of the speed or rate of change of the flux or something, but there will be a rate of change. And because of the presence of rate of change of something, we have the differential equations. And by finding the differential equations, we can figure out what is happening when we suddenly change the torque or the current of the system. Okay, the expected learning outcomes are still the same as before, because for this, the previous lecture, this lecture, and the next lecture, we are basically learning contents that can help us develop equivalent circuit for DC machine and help us use the equivalent circuit to do some analysis. For example, the analysis of torque speed curve and the analysis of how to do the speed control, and also help us assess some of the performance, like the losses and the efficiency. Torque speed characteristics, definitely we are going to explore this, and we are also going to look at the speed control. So these are the learning outcomes. Okay, now let's look at the first topic today, the output power and size of the DC machine. Let's look at the upper left corner figure here. This is the flux lines distribution in a typical DC machine where we have the stator and the rotor. If you look at a stator, the flux lines here is evenly and uniformly distributed. Here is not very uniform, but is approximately uniform. In the rotor circuit, it's uniformly distributed with the same direction, and the flux density is just constant. But in the air gap, is different from this. Well, in the air gap, what we have is the flux is always radially distributed. If you look at those flux lines, and expand them, all the flux lines in air gap, if you expand them, they can go through the center of the rotor, or we see the armature. So this is helpful for us to figure out the developed force, because if you look at a conductor here, the current, then the force of the conductor is supposed to be the current times L cross product B. But because B is always perpendicular to L, what we have is just a simple product, BLI. This is for each of the conductor. And you can find equivalent force for all conductors if the conductors are carrying equivalent current. If the conductors are carrying equivalent current, I, the force is just equivalent to BLI. But assume now we are having a complicated armature circuit where there are a lot of conductors, but each of the conductors will be carrying different current. Then how can you find the total torque? The total torque. Think about this. We have to use the same technique as we used before. Firstly, we try to find out the torque, which is imposed, or we say exerted, on each infinitesimally small part on this armature circuit. And then we integrate them to find the total torque, tau d here. So let's do it. Okay, assume that we have the current, density given as A is the current in per meter length on the circumference of the armature surface. In other words, A is the current density in the unit of ampere per meter, and is per meter distance on the current on the per meter distance on the circumference of the armature surface. And if we pick up this infinitesimally small part, as shown by the red color curve I'm drawing here, is differential element of the current just equivalent to the current density A, that is ampere per meter, times ds. ds is the length of the infinitesimally small part we have chosen. So its unit is meter, and the result is just meter. And if we know this current, we can calculate the force. The force according to F equals to BLI. Now, I is DI, so what we have is just BLA times DS. That's the force. And because for this kind of DC machine, you always have the air gap fluxes in this way, which is perpendicular to the force. The force can be either direction, but it's always in the tangential direction. So your flux density is definitely perpendicular to the force, and therefore the torque, which is equivalent to the force cross product R, is just equivalent to a simple product of force and R, force times R, because they are perpendicular to each other. And that gives us the following conclusion, where the torque exerted on the infinitesimally small part on the circumference of the armature surface is equivalent to R times BL ADS. So we substitute the force equation into this equation. Now R is the radius of the armature, as given in the upper left figure here. Well, we have to say that the flux in the air gap is not uniform, because you see the flux is always in the radial direction, so they are not actually at the same direction, right? Because the flux here is this direction, something like that. So definitely this is not uniform, but it's symmetrical, because For every part of the conductor, you have a symmetrical magnetic flux density. For example, those 2 points are symmetrical, and you can simplify some symmetrical distribution of the flux. And that is trying to help us by giving us a chance to do the average of the flux. So because of the symmetrical feature, we can have an average flux BAV representing the average flux in the air gap. And this is quite reasonable and quite accurate. Now, if we do the integration with average flux density, B average, what is going to happen? Is something like this. Let's do the integration here. Now the integration of, now the integration of D, tau D is just equivalent to the integration of R, because B, we are using the average. Is average value means is equivalent everywhere in the air gap, times LA, both of them are constant, times ds. And we are doing the integration over the surface of the armature. And we can take out all the constants, R times BAV, the average times L times A. Those are all independent of the position on the circumference of the armature surface. Instead, what we are integrating is just ds. And ds, the integration is obviously the perimeter is going to be 2 pi r. So that's what we have here. And we can reorganize the equation in the other way. That is, we take out 2 B average and A. What is left over is pi r squared times L. So what does this mean? If you look at armature cylindrical shape is like this. Now, if we know pi r squared, that is the area of the one surface of the cylindrical shape, and L is the length, pi r squared times L is the volume of this rotor, cylindrical shape rotor. And we can express it by using V represents the volume. Okay, so this expression is equivalent to saying that the developed torque, it is proportional to the average flux density, proportional to A, which is the current density, and proportional to the volume. If you increase any of them, you've got a chance to increase the torque. Of course, increasing the current density is doable, but it is difficult because you have to look at the materials you are using in the current conductor, because each of the material has an upper limit. Second, the average flux density, you can increase it to a certain extent, but if you look at the magnetic saturation of the steel core, I mean the steel used in the stator and rotor, you can't increase it to a very large extent. You can increase in a certain range. Well, what you can do freely is probably this one, the volume. On condition you can accept it, you can keep on increasing the volume. But in most cases, you only increase to a sufficient level. That's all. And because torque is proportional to the volume, and we know the mechanical power, this gross output power is mechanical power. Its output mechanical power is equivalent to the rotational speed of the rotor times the torque. So it's going to be expressed in this way, where we have the mechanical output power also proportional to the volume, average flux density, speed, and A. And as we said, assume we are using the copper in the wire, and it's with a fixed material and fixed cooling conditions. Usually the current density has an upper limit, and we also have comparatively a narrow range of changing the average, increasing the average flux density. But what we can do is to increase the volume or the speed to increase the power. So for if you are asked to select an electrical machine which can develop a certain torque and certain power, you have to look at is volume and speed limit, because the volume affects the developed torque, and both the volume and speed do affect the developed power. Now let's look at the next topic, is the speed control. Okay, if we want to simply represent the DC machine's equivalent circuit, we can write it down in this way, where we have two circuits. Again, this is two circuits, just a simplified version of the two circuits. On the left-hand side one, this is the field circuit. The field circuit produces the electromagnetic field in DC machine. On the right-hand side, this is the armature circuit. Okay. In a field circuit, basically you have, this is a simplified version, but basically you have two components. You have the field inductance, and most importantly, you have a controllable field resistance to control the field circuit. Well, on the armature circuit, usually the Kirchhoff's voltage law is going to give us the armature circuit's terminal supply voltage. This is the external supply voltage. VA is equivalent to RIA, that is the voltage drop across the resistance, plus the induced electromotive force. Here, the full expression of the equation should be VA equals to RIA plus RAIA plus LA times DIA dt plus EA, because we will definitely have not only RA in the circuit, but also inductance here, LA. But that inductance, in most cases, we ignore it, because in most cases, we are looking at not the transient circuit. We are looking at steady state circuit. And in steady state, it is DC, so omega equals to 0, and the L has no impact. So that's why in the steady state analysis, what we have is something like this. The most important thing in the steady state analysis is that we have the electromotive force in this equation, and that electromotive force is equivalent to K, which is a machine construction constant, times the field flux. Here the field flux is given as phi F times the rotor angular speed. For most of the DC machines, especially the high power DC machines, we have very low resistance. Why? Because if you have RA there, you have I square R, power loss. And you know, in recent years, people are emphasizing the efficiency. So we want as much as possible, we want to reduce the power loss. So we want a very small R. If R is small, RAIA is much smaller than the supply voltage, so you can neglect it. If you neglected the resistive voltage drop according to the previous equation, what is left over is just electromotive force. So this, by neglecting RAIA, that is the resistive voltage drop, we have the armature circuit terminal voltage that is equivalent to the electromotive force. And by re-deriving this equation, what we have is just approximately the rotor rotational speed is equivalent to the armature circuit terminal voltage divided by the machine constant K times the field flux. Now, if we have, based on this equation, if we have a nominal terminal voltage and nominal field flux, we'll be able to derive the nominal speed of the machine. This is the nominal speed which is written on the plate of the machine. But interestingly, you can find a phenomenon here. That is, the speed is independent of the torque. Do you think this is physically meaningful? I mean, do you think this is physically true for a DC electric machine? Think about this. I have to say, this is only an approximation. It is not really true because you have ignored the resistive voltage drop, right? And that's the reason why the speed is independent of the torque. Now let's look at this relationship, because we have the torque. Definitely you need to have the torque. That torque is used to drive the load. Otherwise, you can't carry any load, right? This torque is equivalent to K field flux times IA. And we have, if you want to deliver the load, you need a current. And because of the presence of the current, you have a voltage drop, RAIA. And that's after RAIA, you have the induced electromotive force. So if you have a very high load, a very heavy load, you have large torque, large armature current. So you're going to have this part, the armature current voltage, resistive voltage drop very high. So if it becomes high, you can't ignore it. And that's what we were talking about regarding the speed. It's not really totally dependent of the torque. Only when you have a torque current, which is producing a negligibly small RAIA, only at this time you can say that the speed is independent of the torque. And if you look at the lecture notes, this assumption, at the light load condition is always true because the field flux is constant and the rotational speed is proportional to the applied voltage. At light load condition, this is always true because IA is small and IA times RA is just too small. In the one field motor, where we are not using the permanent magnet, instead we are using the electromagnet, it is possible to increase the speed above this speed. To increase this speed above the nominal speed. Why? Because if you look at here, this speed is just equivalent to the IA nominal over K times the nominal flux. But if we reduce the nominal flux to be beneath this value, say half of the value, then you can have a speed which is doubled this nominal speed, right? But still, I would like to mention that you can't, well, theoretically, you can weaken the field to an infinitely small value. For example, you let the field flux approach zero, but this is not really doable for a real machine, because for a real machine, you still have the torque, and the torque is equivalent to K times flux times the current. If the flux is too low, you won't be able to deliver the torque. Even if you have no load on the electrical machine, you still have friction losses and windage. So you can't afford this. If it's the flux is too low for a high speed, then you have a torque which is too low, and this torque will be lower than the load torque. And eventually what happens is that your machine slows down. So it's also reducing the speed. And therefore, we say that you have only a limited speed increase. And also, just now, as we mentioned, you have a developed torque, which is relying on both the flux and the current. If your flux is reduced a lot, you have to increase the current to compensate for this. But if you're reducing the flux too much, this current will not be able to compensate, because there's an upper limit of this armature current due to the material used in the windings and due to the heating ventilation requirement. You have only a limited range to play with. Just now we were talking about in many applications for the DC machine, we can safely ignore the resistive voltage drop, that is IARA, because compared to the terminal voltage VA, it is too small. But if you are looking at small DC machines. When we say small DC machines, basically it indicates low power DC machines. If you are looking at such applications, the small DC machines in low power applications, in many cases, you have to be careful about this because this assumption is no longer valid. Why? Because for low power applications, usually you have low terminal voltage. So if this is low power DC machine, usually you have low terminal voltage VA. And if VA is low and RA is not very low, this relationship no longer holds. So RA, IA will take a certain part of VA, will be a certain percentage of VA, which cannot be neglected. And if that is the case, what we can do is to use the full expression of the Kirchhoff's voltage law. That is in the steady state. Of course, we are not considering the transient because we don't have the inductions here. So in the steady state, we have the terminal voltage, VA, which is equivalent to the sum of the resistive voltage drops and electromotive force. The electromotive force is K, machine construction constant, times field flux phi F times the rotor speed omega R. And we know that the torque is also proportional to the machine construction constant, the flux, field flux phi F, and the armature current. So if you look at those two equations, we have the chance to replace IA by using the torque. Obviously, IA is equivalent to the torque divided by the product of K and flux, field flux phi F. If you substitute this back to the above equation, the Kirchhoff's voltage law equation, what we can have is the terminal voltage VA is going to be a function of torque and also a function of speed. And by doing some simple mathematical manipulation, you move this atom to the left-hand side and you divide K phi F. We have the direct relationship between the speed and the torque. As we mentioned, we are looking at torque speed characteristics. That's why we are keen to find out the direct relationship between the torque and speed. Now, if we look at this expression, you will simply realize that omega R and torque has a linear relationship. And this linear relation is for is because we have an expression like this, omega R, which is equivalent to constant C1 subtracting constant C2 times the torque. And why we say those are two constants? Because if you look at here, usually we don't change the armature voltage. K and the flux, field flux are comparatively constant because K is definitely constant. And flux, if you don't change the field excitation current, is constant. So those two parts, and the resistance is usually constant once you design the machine. So we will have a linear relationship, but this is this linear relationship has a negative slope here. So if you draw it out in the torque speed plane, it's going to be something like this. This is the x-axis is the torque. This is just tau d in our previous equation. The y-axis is the rotor speed. And since we say we have a negative slope line here, it's going to be something like this, something like the blue line here. And the slope, obviously, this slope is proportional to the absolute value of this slope is proportional to RA, because this slope is just equivalent to minus RA divided by K flux square. So if you change RA, you change this slope. Well, you have another way of changing the slope, that is to change the field current, and eventually you change the field flux. But once you change the field flux, you're not only changing this term, but also this term. So it's a little bit more complicated. Okay, now let's look at the no load speed. We know that at no load, what will happen? Think about this. You're looking at a machine. You have a driving torque, T, and you have a load torque. Assume this load torque is tau L. So at steady state, they will be equivalent to each other so that you can maintain a constant speed, right? This is at a steady state because you need to, if you're driving a car, you want this car to move at a speed you want at a steady state. And that means your load torque, your developed torque has to be equivalent to the load torque. But now if there's no load torque, which means the load torque at a steady state is 0, this is what we're going to have. And because we have 0 tau d, which is the torque, we have 0 what? Okay, flux times IA. And the flux is controlled by the flux circuit. So assume that it is not 0. In most cases, it won't be 0. Otherwise, your electrical machine cannot work. So if K and the flux, field flux are not 0, what can be 0? This armature current. So we have the no load speed, which is equivalent to just this part. If you look at the equation here, we have the no load speed that is equivalent to the first term here, because the second term is multiplied by tau d and is multiplied by 0 in no load condition. And we also analyze that in no load condition, we have the armature current equals to 0. Okay, as we analyzed, this is the no load speed. Let's look at armature reaction again. We have been emphasizing these armature reactions because this is really a very important phenomenon of the DC machine. If you look at the armature reaction, we have basically two consequences, as we mentioned at the beginning of this lecture. One of the consequences we already analyzed before, that is because of the presence of armature reaction, the rotor, or we say the armature magnetic field, will distort the stator magnetic field. And if this happens, what is its subsequent consequence? What is the consequence? The consequence is that when the conductors rotate to this vertical surface here, which is perpendicular to the flux linkage, we have the flux linkage not 0. And because of this, we have the electromotive force developed, which is not 0, over the very small internal resistance. Why? Because at this vertical position, we have the commutators short circuiting both the internal and external circuit. For the external circuit, we don't need to worry too much because we have the external circuit's resistance there. But for the internal circuit, the resistance is very small. It's not 0, but it's approaching 0. So we have a huge current. And that current generates the sparks, significantly shortening the life of the brushes and the commutators. This is only the first phenomenon. At this slide, we are going to look at the second phenomenon. So what it is something called unwanted flux field weakening. Unwanted field weakening. Some people also call this flux weakening. You can find both of the terminology in the textbook. So if we express it's going to be unwanted field weakening. And this field weakening's direct consequence is instability. Let's look at the mechanism, why this happens. Firstly, let's look at the upper left corner figure. We know that when we are taking into consideration of the magnetic field generated by the rotor, we will have some part of the rotor generating the magnetic field, which can be projected to be aligned with the stator generated magnetic field. And so some part of the magnetic field is strengthened. Some part is strengthened. Well, some part of the rotor generated magnetic field is going against the stator magnetic field and it is weakened. But if you look at the general picture, I mean, you look at the overall flux, it remains nearly constant. So you might have a conclusion that some part is strengthened, yes, and some part is weakened. So if we add them up, the total flux might be the same. How do you think about this? The total flux density is the same? No, this is not true. The total flux density is reduced. Why? Because we have something called a magnetic saturation. Look at this material here. Well, without magnetic saturation, yes, we can enhance it greatly. But with magnetic saturation, you can only with the presence of the rotor magnetic field, you can only slightly enhance, or we say strength this magnetic field, the stator magnetic field. But when you reduce the stator magnetic field, you can greatly reduce it, because when you reduce the magnetic field, it is not subject to the saturation. So now it's quite clear, right? So when you try to strengthen when the rotor tries to strengthen the stator magnetic field, it only strengthens a little bit, slightly. When the rotor reduces the magnetic field created by the stator, it reduces greatly. So the average effect is what? We have a weakened field. And this is called the field weakening. So, okay, now we analyzed why. When we take into consideration of the armature reaction, we have an average effect of a weakened magnetic field. But you might be questioning that, yes, we have an overall weakened magnetic field due to the magnetic saturation. But what does it mean to us? What does this mean to us? Previously, we mentioned that we have an approximation that the speed, if we ignore the resistive voltage loss, RAIA, we can have an approximation that is the motor speed is nearly equivalent to the armature voltage over K phi. So if you put it here, this is an approximation. If you put it here and you take into consideration of the armature reaction, what is going to happen? Think about this. Your armature reaction reduces the flux. And if the flux is reduced with a constant terminal voltage and constant K, what is going to happen? On R0, the rotor speed will be increased. So if the flux, the field weakening reduces the flux, it will increase the rotor speed. And if you keep on reducing the field flux, it's going to be keep on increasing the rotor speed. This will happen because just now we are only using this approximation to give you a brief illustration. Now let's look at the general picture, which better explains why the average effect of the field weakening will cause some instability. Well, let's look at the equivalent circuit of the armature. RA, we ignore LA, I mean the reluctance, because it's very small. Okay, this is the armature circuit. This is IA. We have two equations. The first equation is established by Kirchhoff's voltage law. That's terminal voltage is equivalent to the induced electromotive force EA plus RAIA. So it's going to be K field flux times omega r. This is the rotor speed plus RAIA. And the other is we have the torque, which is equivalent to K times the field flux times the armature current. So, okay. Now, from this equation, you can see that with a constant terminal voltage, and constant K, assume that currently the current IA doesn't change. If current IA doesn't change, we weaken the flux. So the flux is reduced. We will reduce the first term, right? With a constant. Then in the next moment, I mean, currently we have this equation, and if we don't change the current, instead we reduce the field flux, the first term will become smaller. I mean, this term. If it is smaller, with a constant armature voltage, this term will be bigger. How to make it bigger? RA is fixed, so IA will become bigger. If IA is increased, this term will be correspondingly increased because it's proportional to IA. That means we have an increased torque. And increased torque produces what? Acceleration. And this acceleration further increases the speed, right? That's how it works. And the first impact of the current is to increase the speed, and the second impact is that this current is the current in the rotor. So if it becomes larger, it increases the rotor magnetic field, right? And this increased rotor field means what? A further decreased flux. If we have a further decreased flux, we have a repeating process like this. We further reduce the flux, we further reduce this term, right? If we further reduce it, then with a constant VA, IA will be further increased. If IA is further increased, it has two consequences: further increasing the speed and further increasing the rotor field. And if the rotor field is further increased, the field flux will be decreased again, because we have the stronger the rotor current IA, the larger the armature reaction, and this armature reaction directly leads to weakened field flux. And if that happens, we will have a trend that can be described this way. We have a weakened flux, and that leads to increased IA. IA leads to an increased speed and further decrease the flux, and that leads to further increased IA, and this process continues. So until we reach a speed which we cannot accept because it's too high. If the speed is too high, it's going to cause some mechanical failure. If the speed is too high, it's going to give us some mechanical failure. And that's the point that the machine can no longer work. So from this process, from the analysis we presented just now, and the derivation here, you can see that we are really encountering some trouble of instability because it's causing the failure. So we treat this as instability. What is the solution? The solution is still compensation windings. If we put compensation windings inside the stator, those compensating windings will be creating a magnetic field, which is just enough to overcome the rotor magnetic field. Then we solve the two problems. The first problem is the sparkings and the shortening of the commutator and brushes life. And the second problem is the possible instability caused by unwanted field weakening. Let's look at the effect of the compensating winding in the actual circuit. I mean, look at the effects by using the flux lines and three-dimensional demonstration. Previously, we already looked at the contribution of the compensating winding by using the flux lines. So, okay, let's firstly look at the left bottom figure. As we mentioned, the compensating windings will be here in the stator, not in the rotor. Why? Because it is trying to cancel the rotor magnetic field. That's why the compensating winding is in the stator. Otherwise, it's going to strengthen the rotor magnetic field, right? It's important. And if you have the compensating winding and you have the rotor armature circuit like this, when the machine rotates, you will create a magnetic field as if it is shown in the upper right corner. This upper right corner figure shows us the flux lines. And those flux lines, you can see, they are evenly distributed in the stator circuit here. And when it reaches the horizontal part of the stator circuit, they are not purely evenly, not strictly evenly distributed, but we can approximately say that it is nearly evenly distributed. I mean, the flux lines, their spaces are not differing too much. So you can take the average effect. And because we are using the compensating windings here, they will create a magnetic field which cancels the rotor magnetic field. So it gives us good field magnetic flux lines distribution. This is the contribution of the compensating winding. And you can see that by using them, the flux lines of the field are quite evenly distributed. Although it's not perfectly evenly distributed, but it is okay. The three-dimensional illustration of the contribution of compensating winding. With the compensating winding here, you can see we no longer have the red part here. We no longer have the light blue part, light green part here. So those two parts are actually removed, those two parts. This part, something like this, and this part. So this is the contribution of the compensating winding. Starting of a DC machine. Why would we want to introduce the starting of the DC machine? Because there's a starting problem for most of the DC machines. Think about this. You have a DC machine, and assume this is the field circuit, RF, LF, and you have a voltage source here supplying the field circuit. And there's a armature circuit. You have developed electromotive force, you have resistance, RA, and you have a terminal voltage, VA here. Okay, for the field circuit, because you have a controllable resistor, you can control its current IF. And if you really want a certain RF, you have to assume its terminal voltage is VT. You have to use the relationship VT over RF. You have no other choice, right? So there's a loss there, I square R loss. But for the armature circuit, when you design a machine, you want to reduce the I square R loss, because I square R loss, it increases directly proportionally with the increase of R. So to improve the efficiency, because there's nothing much we can do on the field circuit, to improve the efficiency, what we do is to reduce RA. Because if the RA is small, IA squared times RA is small. If IA is small, then we've got very good efficiency. These days, efficiency is so important, so it is worth doing this. And actually, in most of the DC machines, RA is very small. So to improve the efficiency, RA is very small in most DC machines. And the problem comes when RA is small. Why? Let's look at here. We have the Kirchhoff's voltage law. VA is equivalent to EA plus RA IA. Let's write it as RAIA because we are trying to use capitalized A as the subscript. Okay, IA is here. And now, what is EA? EA is the induced electromotive force is equivalent to the machine construction constant times the flux times IA. The speed times speed. IA, if you want to time IA, is going to be what? It's going to be the torque plus RA IA. And we know that when you start a machine, what happens? Omega R equals to 0. And if omega R is 0, the entire terminal voltage RA, which is quite large in most applications because it needs to support the speed. But unfortunately, at the beginning, the speed is 0. The entire voltage is dropped across RA. So it is going to give us a current like this because RA is very small. But VA has to be large enough for the applications with a high speed. So we have very large current here. Well, is this the problem? If you are looking at a small motor, probably it's okay. Why? Because assume that we are looking at a very small motor. What will happen is that, let's firstly look at small motor. When we say small motor, basically we are saying is inertia is very low. If its inertia is very low, we know J d omega R dt. This is the acceleration of the machine, and this J is the inertia. If we have very small J, we can easily increase the speed because we have a torque developed, and because we have a very large current at the beginning and it gives us a very large torque, which is much larger than the low torque, then we can immediately accelerate the motor. And as long as the motor reaches a certain speed, we have a large enough K flux times omega R, and this is going to consume a large part of the voltage because this voltage subtracting K flux times omega R divided by RA is going to be equivalent to IA. If we have a large enough speed, we have a large enough electromotive force consuming the most part of the applied terminal voltage, then our current can be greatly reduced. This is the small motor. So we only need to undertake large RA for a short period of time. So it's not really a big issue. We only need to undertake the IA large value for a short moment. But what happens if we are looking at a very large motor, say a high power motor? If we are looking at a high power motor, it is troublesome. Why? Because if we are looking at large DC motor, the inertia is high. And for some of them, it can be very high. If it's very high, as we mentioned, this J is too large. And eventually, with the same torque times the omega R, with the same torque, we won't be able to immediately change the speed, even if we have very large torque. It takes a while to change the speed. And if the speed increases slowly, that means the large armature current has to sustain for a while, because your omega r increases very slowly, and in most of the time it is around 0, and it's a very low value. In this case, VA subtracting K phi omega r is still having a very large value, and over RA it is still maintaining a high current. And that high current, if it sustains for too long, say more than a few seconds, it really can degrade the armature circuit, and it can degrade the armature circuit significantly. So this is not really what we want. So think about this. We want a small RA to increase the efficiency, because we can significantly reduce the I square R loss. But the small RA results in the huge starting current. So what should we do? What is the solution? We want small. What do we actually want? We want small RA at a steady state. When the machine speed reaches a certain level. But we want large RA just at the starting process, just at the starting. So what we can do? How can we change RA? So the solution is we insert a circuit, variable resistor circuit, in series with the RA. So by inserting such a variable resistor circuit, at the beginning, I mean, when we are starting the machine, we have RA plus this, assume this is adjustable resistor. We have such a resistance. And when the speed goes up, we gradually cut off this resistance, gradually cut off. And eventually, when omega r reaches the, say, reaches speed, we totally cut off this adjustable resistor. So what is left over is just RA left over. So this means at the beginning we have RA plus the adjustable variable resistor. Then when the speed goes up, we cut off a section of the adjustable resistor. When the speed further goes up, we cut off the other section. And when the speed eventually has been increased to be the nominal speed, or we say rated speed, we have the adjustable resistor totally cut off. That's going to be giving us only the RA left. So let's use a figure to illustrate this case. That is the right bottom figure here. As you can see, we have the electromotive force here. This is the electromotive force, EA, and let's redraw the figure here. We have the, not only this part, we have the electromotive force induced. That's EA here. And we have an armature circuit. This armature circuit has a resistor here. Sorry, the resistor is missing, but you know it is here. So we have the induced electromotive force, we have the resistor, and we have an external circuit that is supplying the external circuit. You can treat it this as VA, but this is the external circuit supplying the armature circuit. And if the armature circuit is like this, we have an adjustable resistor in the system. So when it starts, firstly, we are energizing this electromagnet. Why we are using this electromagnet? Because electromagnet provides some self-regulated circuit. This electromagnet can be self-regulated, so we don't need to put extra control to it. Okay, assume now we start the circuit. If we start the circuit, because we have the shunt field winding providing the field current, which is independent of the armature circuit. And if there's a field current, the electromagnet is energized, and then it attracts this handle to position 1. If it's in position 1, we have the total adjustable resistor. It's going to be R1 plus R2 plus R3 until R4. R1 plus something until R4. And then plus RA. This is going to be the resistance times IA plus EA. Because EA at the beginning is 0, this is equivalent to VA. But because those values are large, much larger than IA, so we have a comparatively small armature current. At least this armature current is within our limitation, within the range that is acceptable. So this is the starting, just the beginning. And now, because we have the current, we have the torque developed, and this torque is going to be accelerating the machine. And the consequence is the speed is increased to a certain value. Once the speed increases to a certain value, this equation changes. We still have this term, but we have changed the electromotive force. That's going to be K flux F times omega R, which is equivalent to VA. So obviously, if you move it to the right-hand side, we have a certain part of VA canceled by K flux times omega R. And because of this, if we still have all the all the parts of the adjustable resistor inside the circuit, the IA will be reduced. So what we do is that once we reach a certain speed, we cut off one section. So how we do this? Say we cut off R1. How we do this? The electromagnet will be further energized, and then this handle will be attracted to this position, position 2. And if it's at a position 2, obviously R1 is cut off because the current at position 2 is flowing in this way. Sorry. It's flowing in this way. It's coming out from the positive polarity, going through R2, R3, R4, RA, and coming back. And then if the speed further increases, it becomes very much larger, then we have another part cut off. So eventually you repeat this process and cut off everything. When it moves to position 5 here, you basically cut off all adjustable resistors. So what is left over is just RA. That's how we start an actual DC machine. Okay, now let's look at the transient conditions of the DC machine. At the beginning of the lecture, we said that what does transient condition mean? Here. Transient, whenever we talk about it, we are referring to the rate of change of something. For example, the rate of change of the speed, the rate of change of the current, and so on. So how would we mathematically express the rate of change of something? dt, something is here, right? And that's and obviously this is a first order differential equation. Now, let's take the speed as an example. I mean, the rate of change of the speed. For example, we analyze it. Assume that now we have a voltage applied to the DC machine. And do you think we can instantaneously change the speed? No. The speed of the machine will not change instantaneously, no matter it's DC machine or AC machine, because whatever the machine is, we have a inertia. And this inertia, if it's large, it takes a while to start the machine, just like our synchronous machine in our power system. If you want to change its speed, it takes, I think, more than a few seconds to change it. It's not instantaneously. Few seconds is already quite long in electrical machine drives and the power electronics. But because of the presence of this inertia, even if you have a reasonably large torque, if you have a very large inertia, the slope of the rate of change of the speed is not will not be very large, because the rate of change of the speed is equivalent to the difference between the developed torque, or we say the induced electromagnetic torque and the load torque, divided by the inertia. And that's why the inertia affects the rate of change of the speed. We know that the developed torque, or we see the induced electromotive torque, it has an equation which is equivalent to K times the flux times IA, where IA is the armature current. And this armature current, this torque equation, if you substitute it into the previously mentioned rate of change of the speed equation, we are going to have an equation like this. You will find that here we not only replace the torque but also replace the replace the current. Why? Because we have a fundamental equivalence established by the Kirchhoff's voltage law. That is, the terminal voltage of the armature circuit is equivalent to the resistive voltage of IA RA plus the induced electromotive force. And this induced electromotive force is just K phi times the rotational speed of the machine. So if you replace IA by VA subtracting this part divided by RA, that's exactly what we get in the middle of the slide here. Well, still, we neglect the inductance of the armature circuit. Why? Because we want to simplify our analysis. Think about this. Now we are looking at the rate of the change of the speed. And what we have is something like this. This is what type of equation? This is already a first order differential equation, because we only have the rate of change of one variable. So it's a first order differential equation. Now, if we consider the armature inductance, what is going to happen? Because armature the armature voltage is equivalent to RAIA plus EA. But if we consider, this is by neglecting the inductance. If we consider inductance, we have LA times DIA dt. Another differential equation. So if we consider the inductance of the armature circuit together with the rate of change of the speed, is going to be a second order differential equation. It's going to be more difficult to solve it. So to simplify our analysis and to make it easier to solve, we firstly ignore the armature inductance, which is reasonable, because in many cases the armature inductance is not very large, and even if you analyze its dynamics, you can rely on some computer software. Okay, now let's make a further assumption, which further simplifies our analysis. In this equation, on the right-hand side, we have two terms, the developed torque and the load torque. Now assume that we have no load. If we have no load, what happens? The load torque tau L equals to 0. This is our second assumption. And if tau L is 0, obviously this equation cancels this part, can be rewritten to this form. Because we have, if you look at original equation, at no load condition, we have rate of change of the speed, and we have the speed itself, right? if you reorganize this equation, it's going to be, assume this is a constant A times rate of change of omega r times omega r equals to another constant B. So it's something like this. A is a constant times omega r derivative plus omega r equals to B. How do we solve this equation? Think about this. How to solve this equation? We have two methods to solve it. The first method is to solve it in time domain. And in time domain, what can we do? We are looking at something whose derivative can be a linear function of itself. And one of the typical examples is exponential function, right? Because the exponential function, its derivative is what? Itself, right? And obviously it meets this condition. So the derivative of something is equivalent to a constant subtracting itself. So it's some sort of exponential function. And if you assume that this is an exponential function with omega r, for example, equals to c, a constant times e, for example, it can be a function of time, so probably is a time. You can substitute this general solution into the equation here and try to figure out what is c and what is a. But eventually, if you do this, you will find that the final form is not like this, but it's something very similar. That means you have to make another guess, and what we have is something like this in the time domain. What we have is something like this. The omega r, which is equivalent to a constant. V is the terminal voltage constant over K flux. K is the machine construction constant. Flux is the field flux. So this part is a constant. We can express it as nominal speed times 1 subtracting E with the power minus T over tau. So this tau is terminology is called a time constant. You will, if you haven't learned this concept, I don't want to further confuse it. Time constant means something that you will hit after this time constant, you will reach a certain level of the final value of the function. You will definitely learn this in the future in control engineering. Probably you have already learned this, but anyway, it is a time constant, this tau. So the speed, if you figure out its solution, is going to be a constant, which is the nominal speed times 1 subtracting E with the power minus T over time constant tau. And what is tau? You can figure out. Its equation is like this. But pay attention here. This one is not small j, it's this j. It's inertia. So tau is equivalent to RA. RA is the armature resistance times J is the inertia over K phi square. Okay, this is what we get for the time constant, and subsequently this is the speed. Just now we said this is the first method of solving the equation. Then what is the second method? We are using the frequency domain. We can use the frequency domain. For example, Laplace transformation. If you do some Laplace transformation, what does this function look like? A times d dt means S omega r plus omega r equals to B. So obviously AS plus 1 times omega r is equivalent to B. Omega r is just B over AS plus 1. Now at this stage, you do the inverse Laplace transform. You can use computer. For example, you can use the software MATLAB to do it. It's very simple. You key in all the symbolic representations, and it's going to help you solve the inverse Laplace transformation. And that's going to give you the same solution as here. So you can find the solution either in time domain and in frequency domain. Actually, I recommend the frequency domain, but because the Laplace transformation mathematically is very easy to derive, and you can always use the lookup table given to you, or you can use the computer software to easily find out the answer. Just now we were looking at the the speed of the motor, and we figured out is a solution to its first order differential equation. Then what about the current? What is the armature current? Think about this. What is the armature current? Well, if we still ignore the armature inductance, still ignore the armature inductance. Obviously, if you want to find the armature current, you can't use the first order differential equation of the armature inductance when you ignore it. So what you can do is you try to find the torque, because the torque is equivalent to K phi IA, right? And what is IA? Oh, sorry, you're trying to use the voltage equation actually. The voltage is equivalent to RA IA plus K flux omega R, because you know the time domain expression of omega R, and IA is just equivalent to K phi. It's going to be equivalent to VA subtracting K phi. Omega R, we know that the expression of omega R divided by RA, that's going to be the IA equation. Sorry, you don't need to use the torque. Instead, you need to use the Kirchhoff's voltage law, using VA subtracting K flux times R omega R, where omega R you already obtained from here. You already obtained the expression of omega R from here. Substitute it into the equation here, divided by RA, you get the expression of IA. And if you know both of the time domain expressions of IA and omega R, what you can do is to plot them out in the time domain. Let's look at their plot out in time domain. This is a normalized plot where the x-axis is the time, but the time divided by time constant. So you can see the time is 0 times the tau, 1 time tau, twice tau, 3 times, and so on and so forth. Well, on the y-axis, it is still normalized current and speed with respect to the rated speed and the rated current, always in nominal speed and nominal current. So let's firstly look at the beginning. At the beginning, the time is 0. So obviously, at this time, we have no speed. And you can also read, you can also find the information from this equation, because when t equals to 0, this part is what? E with the power 0 is 1. So this part is 0. So you have 0 speed. That means at the beginning, you really have a 0 speed. This is speed curve. But what about the current? For the current, when t is 0, IA is equivalent to IA 0 times E with the power 0 is what? It's 1. So times 1. That means it's IA 0. So IA 0, if you normalize it by IA 0, it's going to be 1, right? So speed starts from 1, current starts from the nominal current. Now, as the time goes on, because we have two exponential curves, one is the current that is exponentially decaying, obviously from manners of the power here. You can see it's exponentially decaying, and it keeps on decaying like this. Well, for the speed, it is exponentially increasing. Why? Because is one subtracting this exponentially decaying part. So it's going to be exponentially increasing until it reaches the rated speed. What does this mean? Because when the time approaches infinity, E with minus t over tau is what? 0. Or we say it approaches 0. If it approaches 0, one subtracting a variable which is nearly 0 is giving us that omega r is approaching omega r0. That's the rated speed. So it infinitely approaches the rated, or we say nominal speed. And at this time, if it reaches the nominal speed, what is going to happen? The current will approach 0 because we are looking at a no load condition. If no load condition, you reach your destination speed, the torque is nearly 0 and the current is 0. And you can also read it from here. When t approaches infinity, because E with this part, minus t over tau is nearly 0, so IA approaches 0. And that's exactly what we see here. Okay. This is the transient analysis, and let's summarize what we have learned today. Firstly, we look at a relationship between the output power and the size of the DC machine. We realized that the torque of the machine, the developed torque of the machine is proportional to the volume and several other factors, for example, the flux density. And the output power of the machine, the output mechanical power is also proportional to the volume. So by increasing the volume, you can increase the two. Or if you want to keep the volume as constant, but increasing the torque or increase the power, you can manipulate the other variables, such as the average flux density. Next, we looked at the speed control of the DC machine. We realized that the torque speed characteristic curve is a decaying, is having a negative slope. And this negative slope means when we increase the torque, the speed has to decrease. And we can do some speed control to compensate for this and bring back the speed. Next, we look at the three-dimensional demonstration of armature reaction compensation. With the compensating winding, we have seen an evenly distributed armature evenly distributed magnetic field with the armature compensating winding. And therefore, we can avoid two things. The first thing is the armature reaction induced huge current in the internal circuit because of the electromotive force over very small resistance. And the second thing is that armature reaction causes a generally decreased field flux. If the flux decreases, it's going to increase the speed and the armature current. If the armature current increases, it further decreases the flux, and this trend goes on, causing some instability. And we said that armature reaction can be compensated by field winding, and with the field winding, we solve both of the problems we were mentioning just now. Starting circuit. Most of the DC machines we mentioned, they have very small resistance, armature resistance, to improve the efficiency because I square R loss has to be reduced. Therefore, the starting current will be very high. So we put adjustable resistance in series with the armature circuit at the starting point, and then eventually we gradually cut off this added adjustable resistor. The transient of the DC machine, we basically look at the rate of change of the rotor speed, and the rate of change is equivalent to the developed torque subtracting the load torque. We try to solve the first order differential equation when we have nearly zero load torque, and subsequently we find out the exponential expression of both the armature current and the speed. Okay, that's all for today. Thank you.